Hello YouTube, welcome back. Would you like to know how to solve an equation using Newton's method? If so, you might want to watch this. Okay, let's get started. So we are going to solve a fairly simple equation using Newton's method. So I've got this booklet which is available on my website, and the link will be in the description below. Okay, and it's freely available, so let's move on to the question or the area that we'll be looking at, which is page 111, 112. Okay, so these two questions are numerical methods, all right? But I think I'm going to leave these two particular problems to you, and I'll do a different one that I've just made up. Okay, so what we are going to do is a problem which I've got. So we'll say f of x, we're going to solve f of x is equal to cosh of x plus x squared minus 3x minus 4 is 0. All right, so we're going to seek the zeros of this function. Okay, but so you might first want to plot the function to see what you're looking for. All right, and Mathematica allows you to do that, so let's do it. So we want to plot this function right here, so I'll just copy it out. Okay, and let's plot it between -3 and 3, for example. Shift enter, see what we have. Okay, it looks like there are 2 zeros in this range. Right now that might not be all of them, but let's just use this and see if we can find. Let's choose one. Let's try to find this 0 down here that looks to be around 2.4 or so. Okay, so now what is Newton's method all about? It is a method to help you find one of the zeros of this function, but what it does is it finds an approximation of a zero of the function based on your guess. All right, so if we were, for example, to guess x equals 2, what it would do is find a better approximation for you if all is going well and the method goes as planned. We have to say that there are some potential problems which we can talk about later. Okay, but it's a fast method for finding the roots of a function, because unlike the bisection method, which we did in the session before last, Newton's method is converging quadratically when it works, right? Whereas the bisection method is a rather more robust method for finding the zeros of a function, but it converges linearly. Okay, so let's describe geometrically how this works. All right, so if we are to guess a point that is near a root of the function or 0 of the function, we might guess, for example, x equal to 2. All right, so if we did that, then we'd have a y value here, and you can see it would be negative in this case. So let's find that. All right, so I can copy this, and I can say replace all in order to avoid putting the number 2 into memory as x. Okay, so replace all, and I'll say x goes to 2.0 so that I get the numerical value that I'm after. Okay, shift enter, and we'll see. All right, so you can see that this number down here on the y point is -2.2378, and so on. Okay, so we'll copy this, and let's come down here and call this the point P. All right, so P equals 2.0, comma, minus, and let's chop this off. right about there, so that's roughly good enough. Okay, now there's going to be a point here, right here, where we draw a line through the point we've just found, P. We take a tangent down towards the axis and see where that takes us if the y value of the tangent line on the other end is equal to 0. In other words, on the x-axis. Okay, so let's construct this visually so we can see it. Okay, now, well, I'm going to tell you the other end of that tangent line because I've already got that. So I'm going to say Q is equal to the point 2.48, comma 0. All right, now I got this using Newton's method, but let's just have a look at these 2 points when we connect them with a line. All right, so next I'm going to write, all right, so I want to create an array containing those 2 points, P and Q, and I now want to plot them. Okay, so let's plot them. So we'll write list plot. And then we want to increase the size of the points when we show them on the graph. Okay, so let's write plot style. Yep, style with a T. And then an arrow. Okay, I put a minus and greater than sign, and then I press the space bar. Okay, and then I'm saying point size 0.02. That seems to be about right for making the points look big. All right, now let's so this is a graphic that I'm building, right? So let's go up here to this spot, and I'm going to call this graphic where I plotted, let's call that A. Now we put a semicolon around it because I want to show the two of these together. All right, and next let's call this one down here that we're just building, let's call it B. Okay, and down here we'll come down and write show A and B together in the same graph. Okay, shift enter. Let's see what we have. Okay, so these are the 2 points that I was talking about. Now you can see this one is not quite on the curve anymore, right? It is on the x-axis, but not on the curve. I found it by taking a tangent at this point 2, comma, minus 2 point, whatever it was, 48 or so. All right, now, so that we can see this even better, let's draw a line between the two of these. Okay, so now I want to build another graphic, and let's call it G because I can't call it C. G looks a little bit like C, so okay. Now I want to put line from P to Q. All right, but this is just giving me a raw graphic object line, so I need to show this as I need to say that this is a graphic, so I'll write graphics. Yeah, graphics. Okay, and then semicolon. And I want to show this as well, so I'll include this down here in show. Okay, shift enter and see what we have. Okay, now you can see a little black line there. All right, little black line. So because we know now we're interested in finding this using Newton's method, this point over here on the right, let's narrow in on this so we can see it a bit better. So let's plot this instead in the range from 1 to 3. Okay, so we'll go up here and change this -3 to a 1 and do this again. All right, now you can see this actually is a tangent line. Okay. All right, but so the idea behind Newton's method is you make a guess, all right? You take a guess, evaluate the function, construct a tangent line, right? Where I'm circling this point right down here, construct a tangent point at that point, and you follow it down to the x-axis. Okay, you find out where this tangent line intersects with the x-axis, and then from that you obtain a new point. All right, so notice that this new point is closer to the zero of this function than your original guess was. All right, so most of the time that's the way it goes. All right, so now we have the point 2, comma, and then the value of the function at 2, right? That's something easy to get. And also we have the y coordinate of this point, 0. Now, I gave you the x coordinate of this point because I had already found it, right? But now let's construct how this works geometrically. Okay, or sorry, algebraically. So we've done the geometric setup, right? We've described the geometric setup. Now let's consider how this works algebraically. So you want to think geometrically and prove algebraically. So let's do the algebraic part. So we start with a point. Now that was x0, which in our case was 2, and then f of x0. Okay, so I'm writing now code that I don't plan to execute. I'm just thinking of a way to describe this to you. So I'm just writing in this now. Okay, so we got one point, and let's call this P is this. So I'm using a lowercase, so it appears blue. And then Q is equal to x1. And then the y coordinate of that is 0, right? Okay, so we want to solve for x1, basically, using algebraic methods. Okay, now let's construct a line. All right, now I'll use uppercase letters x and y to suggest that I'm thinking of these in a different way. All right, so we've got the line y equals mx plus c. Okay, so this is just a generic line. Now we know what m is. M is f dash of x0, right? Okay, we know that because we're following a tangent line, and the slope here is f dash of x0. Okay, so now we have this point up here, P, which we can use in substituting into our equation. I better scroll down so you can see this. Okay, so we can substitute this now. All right, so let's write. I'll copy this, paste, and what I'm going to do is sub in x0 for x and f of x0 for y. Okay, now notice that gives us a way to solve for c. All right, so I can take this right here over to the left-hand side by subtracting it from both sides. Okay, so copy, get rid of it, subtract, put it here. All right, so I've just done some algebra, and notice what we have is c is equal to this. Okay, so c is this. Okay, now we'll come down here and use this in our description of the equation to replace c. Okay, so c is now this expression. Okay, so now we have an equation, a linear equation where we know c, and this is the equation of our tangent line. All right, now that we've got that, so let's state what we've got. Tangent line is this. Okay, now we have another point. We have the point Q, right? So let's use that to solve for x1. All right, so we have y equals 0. Okay, so let's say what we're doing. We are using this point Q. Okay, so now I'll copy this equation, come down here, and we have y is 0. Okay, so 0, and we have x is x1. X is x1, and now let's just solve for x1. Okay, so to do that, we can take this and put it on the other side by subtracting that from both sides. Okay, so let's say what we're doing. Solving for x1. Okay, so we'll copy this, put it down here. Now we wanted to take this over to the other side, but to do that we've got to make it negative. Okay, so paste over here, make it minus, and then change the sign of this one. Okay, and then finally I can divide by f dash of x0 to get x1. Okay, so let's come down here and say dividing. All right, copy, paste. We're dividing by this on both sides. Okay, so copy, and I can get rid of it. And then, well, okay, I'll write all of this over f dash of x0. All right, now when I divide this into what's in the brackets, what will happen is this f dash of x0 will cancel with this one, and then we'll have minus f of x0 over f dash of x0. Okay, so I'll copy this, and I'll expand this division into the brackets. Okay, so over that, and then this one gets divided away, and then we have this gone. Now we can get rid of the brackets and make this look more attractive. Okay, so it will say x1 equals this right hand side. All right, but it's nice to put the minus in the back. So let's do that, put the minus in the back, and then this is what we have. Okay, so now we have an equation for x1 in terms of x0. All right, which is good. Okay, so let's reiterate what we have. Let's say a better approximation of a 0 should be x1, and that is given by this expression. Okay, but now what the idea here is, once you found that, let's go up and look at the geometric picture. So once you found this point, and you do so by finding that x1 from x0, then you can take that and repeat the process. All right, so you can repeat the process. Now what you would do then is come up here to the value of the function at x1, take a tangent, follow that back down to the x-axis, and get another point, x2 comma y2. All right, now you don't do this geometrically every time, you just use your algebraic formula for that. So now let's say, well, instead of always obtaining x1, what we can do is write a general formula for this. All right, so we'll say in general, this might be n plus 1, this would be n, this would be n, this would be n. So in other words, we have a recursive formula for what should be a better approximation to a root of the function based on a previous term. All right, so let's say in general, a recursive sequence of points that are supposed to be better approximations of a 0 of f of x. Okay, so that's what this sequence does. All right, so we've constructed this geometrically. Now, Newton's method also works for systems of equations. All right, so if you want to think about systems of equations, it's better to think about this sequence derived using the Taylor series instead. Okay, but for our purposes now, since in this session we're only going to consider Newton's method for an equation of one letter x, solving that, well, the geometric method is just fine for this. All right, and it's because you have the visuals, it's more descriptive in that way. So this is good. All right, now that we've derived it, basically what should be a better approximation of a zero, let's implement it. Okay, so now right, so here's a, we need to build a function. Okay, so let's build a function now. Since maybe you might want to use another programming language, maybe one day, like Python, for example. It might be good to think about these in terms of building functions. Okay, so let's do that now. Okay, so let's say Jim is a function of x. Okay, colon equals, right, module. Put in a spot for our local variables, but we don't need any. Okay, so we want to write the function now. That was cosh of x plus x squared minus 3x plus 4. All right, good. Semicolon. All right, now let's think of a female name. Well, first of all, we want to calculate the derivative of this, so let's do this symbolically. Okay, so to do that, you just put D, uppercase D, copy this, put it here, and we want to differentiate with respect to x. All right, so let's do this. Go down here and find it. It says C is protected. All right, I see. I've executed all of this, but really this should have been a comment. Okay, so let's put all of that discussion in a comment, and that ends right about there. Okay, now because I've put a bunch of things in memory that I didn't want to, I've got to go and quit the kernel. So quit the kernel, local, quit. And then since I've done that, I want to do a rather simple calculation, like add two numbers just to start the kernel again. And it takes a little while the first time. Okay, so yes, now we can get rid of this and get back to our calculation, differentiating that function. Okay, so here we have the derivative of f. So this is f dash. So copy that up, copy it, and I'll put it back here. So I'll just comment this one out because we don't need it. All right, so I'll paste the derivative. I want to construct a function. Let's call it Sarah. Right, I think that's how you say Sarah in Italian. All right, module, empty brackets, in that there, semicolon, shift enter, so that's in memory. All right, that's the derivative. Okay, now we want to run this sequence. So we need minus Jim of x over Sarah of x, and then we subtract that from x, right? Okay, to do this. So what I'm doing now is building a function to do this part of it. Okay, so let's pick a male name, Dino of x colon equals module okay, so this function Dino should return the next term of the sequence. All right, now it's a good idea to try it out before you start running a while loop or a for loop or something like that. All right, so let's try it. So we'll write Dino of 2.0, and we should get the next x term in the sequence, what we found up here in our diagram, around about 2.5. Okay, so hopefully if it works, that's what we'll get. Shift enter. 0.75. Well, is that what we're... Okay, so I found the problem. We should have had a minus right here at the -4. All right, so this is our function gym. Shift enter. All right, let's have a look. Dino 2.4836. Very good. Okay, now that we're confident that Dino is the correct function to give us the next term of our sequence, we're now ready to construct a while function. Okay, so the basic structure of a while function is there's a test. All right, so the test comes first, and then you say what to do. All right, now you have to basically iterate over something, so you might do so with n equals 1 to start with, and then we'll say n increases by 1 in every term of this sequence. But the difference between a while loop and, say, tabulating is when you tabulate, you are keeping all of those things in memory and generating a list, right? Which is perfectly fine so long as you don't need to fill up the memory of the computer. But generally, it's good practice to use something like a while loop. Okay, so now the test will be, is the next term in the sequence close enough to the previous term? All right, so let's write ABS. All right, now let's call the next term in the sequence, which is xn+1. Let's call it z. Okay, so z minus x, and x being the previous term. All right, so while this is greater than the tolerance, and let's just put TOL, and then we'll set a tolerance. Tolerance equals, try 0.001. Okay, and then we can start with x equals 2.0. All right, now look, Dino doesn't have the precision. Is the numerical part of it is set here, right? Because we put in a decimal place. All right, but what we can do is say that instead we want to take this to 50 decimal places, for example. All right, so let's redefine Dino in that way. All right, so while the absolute value of these two is greater than our tolerance, then we want to do something. Okay, so we want to set x equal to z. All right, this turns x into the next term, and at the same time we want to put z equals Dino of x, and we want to see what's coming out of this, so we'll print x. Okay, so that's the basic structure of our while loop. Now we're missing one thing, which is to up here say z is equal to the next term in the sequence that we started with. Okay, so Dino of 2.0. But we can just put x in case later we need to change this. All right, so I think that's good, and now let's try this out by pressing Shift and Enter. Shift Enter. Okay, and what comes out of this are 4 terms of the sequence of approximations of a better approximation of a root or 0 of the function. All right, but we've only got about 5 decimal places, so something is wrong there. Let's extend the tolerance, make it smaller. Okay, so if you want to get more precision out of the calculation and make good use of the tolerance, so all you have to do is change the x from 2.0 to just 2. Okay, and then Shift Enter, see what we have, and now we see we have a whole lot more precision in the calculation. All right, and so we can see this converging all the way out to say as many decimal places as you like. All right, now we got a lot of terms. And yeah, you can see this converging to great accuracy. Okay, so that's all for now. I'll see you next time. Thanks.